Hey everyone, this is hopefully a quick video for problems 7, 8, 9, 10, and 11 that are on the aspartic acid handout. And so here's problem number 7. It asks what pH would be the monoprotic form be present at the highest concentration. And our monoprotic form is HA minus, right? And so we can see that it lies between pKa2 and pKa3, so our pH is going to be halfway between those two pKa values. And when you do the math, 1/2 of parentheses 3.9 plus 10.002, you get 6.951. In a similar way, in problem number 8, the question is, at what pH would the diprotic form be present at the highest concentration? All right, and so when we think about that one, we're thinking about this guy right here. And so you can see that that is halfway between pKa's 1 and 2. And when you do the math, you get that the pH at that spot is 2.945. All right. Then when we think about question number 9, we got to do a little more math. So the question is, calculate the pH and the concentrations of all of the aqueous species, including hydroxide, in 0.1 molar aspartic acid hydrochloride. So we first have to disentangle what is aspartic acid hydrochloride. So to figure this guy out, aspartic acid itself, just regular aspartic acid, is going to be the electrically neutral one of the 4 species, so H2A. And as a result, the chemical compound that we're talking about with aspartic acid hydrochloride is going to be the H3A plus. So we've got a 0.1 molar solution of H3A plus. Okay, so when we think about that, that's the fully protonated form, H3A plus, and as a result, this is going to be treated as if it were just a simple monoprotic weak acid. And we'll do that for the beginning part of the problem. We'll pretend like it's a monoprotic weak acid for the purpose of calculating a few of the concentrations along with the pH, and then we go back to our normal understanding of the fact that it really isn't a monoprotic species. It's got 3 protons on it. And so we'll figure out H3A plus, H2A, H plus, and hydroxide and pH from the monoprotic assumption. And then we'll forget about that and we'll calculate HA minus and A2 minus by recognizing that in fact it does dissociate a second, a third time. So our overall approach then looks like this. We start with the first dissociation reaction, pretending like this is the only one. And we've got this reaction. We know that our Ka is going to be, looking it up in the back of your textbook, or you can even calculate it from the pKa, but I use the number in the back of the text, 0.0102, and that's going to be x squared over 0.1 minus x. Right, there's our overall setup. And then we do our solve function to get our concentrations of each of the species. We know that, whoops, sorry, I hit one of the accidental keys there. So we know that X here has a definition. H plus concentration is X, and that's going to be 0.027 molar rounded. And then also we know that the concentration of the diprotic form, the conjugate base of H3A plus, is also X, 0.027 molar. And we can calculate the concentration of the H3A plus itself, and it's going to be the original formal concentration minus X. So 0.1 minus X gives us 0.073. And finally, we can get hydroxide from the H plus concentration, Kw over X, And when I did that, I got 3.7 times 10 to the minus 13th. All right, so that gives us all of the values we can calculate by the original assumption that it's a monoprotic weak acid, which it actually isn't. So now we have to recognize that it's really a triprotic thing. And so we've got to look at the calculations of the other concentrations from the other dissociation reactions. So from the second dissociation, H2A makes HA minus and H plus. We know that Ka2, which we can calculate or look up the value in the back of the text, is going to be HA minus times H plus all over H2A. All right, we recognize that we know the H plus concentration, and that's right here, 0.027 molar. We know H2A. That concentration is also 0.027 molar. And because those two concentrations are the same and they're in the numerator and denominator, they cancel. And we see that HA minus concentration is going to be equal to or very close to Ka2. So that value ends up being, looking it up, 1.26 times 10 to the minus 4th. Molar. So HA is 1.26 times 10 to the minus 4th molar. Here, it's probably better for me to write it like this. Okay, then we make the final assumption from the final dissociation reaction. And we've got HA minus dissociating now to make A2 minus, the fully deprotonated stuff, and H plus. Ka3 describes that, and it's going to be A2 minus times H plus all over HA minus. And we, again, recognize that we can look up the value for Ka3. We know H plus already from up here, 0.027 molar. We now know HA minus because that value is Ka2, and it's also given right here above. But anyways, this value is Ka2. And so we can rearrange this to get the concentration of A2 minus is simply going to be Ka2 times Ka3 all over X. All right, again, we know all those numbers. And when we do the math, we get 4.6 times 10 to the minus 13th molar. Finally, the only other value we need to calculate, and it isn't a concentration, is the pH. So we're simply going to use our H plus concentration and take the negative log. And when we do that, we get our pH of 1.56. So that's how you do problem number 9. Let's go to the next problem. So here's problem number 10. And in this particular problem, we've got our pKa diagram again already for us. Calculate the pH and the concentrations of all the aqueous species. And this time we have a 0.1 molar solution of the monosodium salt of aspartic acid. So monosodium salt of aspartic acid, we again think about the fact that aspartic acid is H2A. So the monosodium salt is going to replace one of those H's, and we've got a solution of HA minus. So for number 10, that's how we start. And the concentration is 0.1 molar. So when we do this problem, we first think, since it's an intermediate, an amphoteric intermediate, the pH of the solution is going to be halfway between the two appropriate pKa values. And since this is our compound, we're going to use pKa's 2 and 3. And so our pH halfway between those two values is 6.951. And that's going to allow us to get H plus. 10 to the minus 6.951 gives us 1.12 times 10 to the minus 7th molar. And if we needed it, we won't use it for any more calculations, but it says to calculate everything. So hydroxide here gives us 8.93 times 10 to the minus 8th molar. That's using kW. Okay, now finally, to do all the rest of the concentrations of everything else, to get A2 minus and H2A and H3A plus concentrations, we've got to make an initial assumption that we'll test at the very end. And that initial assumption is that we're going to assume that the formal concentration, which in this case is 0.1 molar, that formal concentration is the final equilibrium concentration of our HA minus that we originally dissolved. We don't know if this is actually going to hold true after we do our calculation, but this is how we have to start in order to be able to get some values that then we can test at the very end. So now we can go to each of the equilibrium reactions. And if we're talking about HA minus and we know its concentration to begin with, then we're going to think about the third dissociation and the second dissociation because they both contain HA minus, and we'll see that we're just missing one value from each of those. And you'll see what I mean here. So from the third dissociation, HA, oh, just a second. So from that third dissociation, HA minus makes A2 minus and H plus. We've got the expression for Ka3. And we know already this value. We know already this value from up above. We know the Ka3, and we can just substitute and get A2 minus. And when I do that, my A2 minus value is 8.88 times 10 to the minus 5th. Similarly, from the second dissociation, and Ka2, we can write that expression. And once again, we know 3 of the 4 values present in this expression. We know H plus from up above. We know HA minus from up above at 0.1 molar. We know Ka2, so we can solve for H2A. And when I did that, that value is 8.89 times 10 to the minus 5th. And this brings me to just a little sidetrack point, and that is that whenever you have a solution of an intermediate, in this case HA minus, the concentration of its conjugate base and the concentration of its conjugate acid, these two concentrations on either side of HA minus will often be extremely close in concentration to each other. And as we can see, 8.88 times 10 to the minus 5th and 8.89 times 10 to the minus 5th. All right, finally, we want to get the concentration of H3A plus. So that's going to come out of the first association. And then we can write that dissociation expression down here. And again, we've got 3 of those 4 values. We've got H plus. We now have H2A from up above. And we've got Ka3, and we can solve for H3A plus. And when we do that, we get 9.76 times 10 to the minus 10th. Okay, now finally, I've run out of space, so I'm going to erase some stuff. But now we have to test our original assumption. And here's our original assumption. We're saying that virtually all of the 4 forms of the aspartic acid, all of them are pretty much just going to exist as HA minus, and all the other concentrations of all the other forms are very small. Let's see if that's true just by looking at the numbers. We see that the concentration of the fully deprotonated A2 minus is very small. We see the concentration of the diprotic form, very small. And we see that the concentration of the triprotic form is really, really small. So our initial assumption looks like it's right. Now we have to do the math. So I'm going to erase this bottom part just so we've got a little bit of space. And you've already got your numbers written down. So here's our assumption that 0.1 molar, we know the formal concentration is going to include all of the concentrations of all the species. So we can just rearrange this, because what we're saying is, what is the final concentration of the HA minus? This is what we want. And we have calculated values for A2 minus, H2A, and H3A plus. So we just do a little subtraction. And we know that the concentration of HA minus is going to be 0.1 minus 9.76 times 10 to the minus 10th minus 8.89 times 10 to the minus 5th minus 8.88 times 10 to the minus 5th. And when we do all that math, we get the value 0.0998. But we realized that we started out the problem at the very beginning, way up here at the top, with 2 sig figs of formal concentration. And as a result, we really can only express HA minus to 2 sig figs. And when we round this value at the bottom that we just got to 2 significant figures, we see that HA minus rounds to 0.1 molar. That's the end of that problem. All right, final problem is number 11. And in number 11, we've got a solution at pH 4.20. So where are we? We're right about here in the pKa diagram, and in the concentrations of all the species. What we can see is that we're within 1 pH unit of pKa2. So this solution is a buffer. All right, if the solution's a buffer, then what are the conjugate acid and conjugate base pair at 4.2? And when we answer the question about this buffer, we'll actually get the answers really to questions A and B. So which form predominates? Well, at this spot, we've got a buffer where HA minus is the predominant species. And the other species present in this buffer is going to be our H2A. We're going to have less of it. Okay, so then for question C, what we know is that if we've got a buffer and these two are predominant species, there of course will be some A2 minus and some H3A plus in the solution. But at this pH of 4.2, there will be very little H3A plus and A2 minus. And we can assume that those concentrations, though they're present, the concentrations are negligible. And so because they're negligible, we're going to make a really great assumption and an approximation that those two concentrations for part C, HA minus added to H2A, make up nearly all of that 0.1 molar formal concentration. And that same assumption says that A2 minus and H3A plus are negligible. They're there, but very small. Okay, if that's all true, then we can use the buffer equation to do the concentrations of all of the different forms. So part D looks like this. It starts with the buffer equation, pH equals pKa plus the conjugate base over the conjugate acid. So pH is 4.2. And the pKa that we're going to be dealing with is the 3.9 value, because that's the pKa within this buffer range. All right, and then we've got the conjugate base over the conjugate acid. All right, and that conjugate base is going to be our HA minus. Conjugate acid H2A on the bottom. Now we have to make this part C assumption into some algebra. So what we're going to say from part C is that let's let X be the, how did I do it here? Let X equal HA minus. And if that's the case, then 0.1 minus X is going to end up being H2A. And now we've got just one variable and we can plug things into the pH equation. So 4.2 is 3.9 plus the log of conjugate base on top. That's X. 0.1 minus X on the bottom. Solve for X and we get 0.0666. All right. And so that means that our HA is 0.0666 molar and H2A is 0.0334 molar. Cool. So we've got two of the concentrations figured out. And we also can easily just take our pH and make it into H plus concentration. So our H plus concentration, we also actually know. That value is 6.31 times 10 to the minus fifth molar. And if we wanted to, we could calculate OH minus. All right, so we've got some really important numbers here. We got the H plus concentration, and then we've got these two values. And what we can see is that we can now write the acid dissociation number 1, and we can write acid dissociation reaction number 3, and then figure out the concentrations. Even though we're saying they're negligible, we can figure out the concentrations of the A2 minus and the H3A plus from those two reactions and from their equilibrium expressions. So when we do that, here's what happens. From H3A plus makes H2A and H plus. Our Ka1 describes that, H2A, H plus, all over H3A plus. All right, we saw from our previous calculation that we know the value for H plus. We know the value for H2A. Whoops. Not sure what I just did there. Anyways, we know the value for H2A. There we go. Oh. See what I'm doing wrong. I'm writing too high on the page. All right, there we go. We know that guy, and we know Ka1, so we can solve for H3A plus, and that value ends up being 2.1 times 10 to the minus fourth. All right, and that is 0.00021, so it's pretty close to being negligible in terms of our assumption. From the third dissociation then, HA minus makes A2 minus, and H plus, our Ka3 is going to be that. And again, we know our H plus, we know our HA minus, we know our Ka3, and we can calculate A2 minus. And when I did that, I got 1.05 times 10 to the minus 7th molar. So in a nutshell, those are problems 7 through 11 on the aspartic acid handout. Thanks for listening.